Okay. So let me thank the organizers for inviting me and giving me an opportunity to attend this conference. I have met Professor Ramamurthy various times since I joined for PhD in math science, and I have always found him very friendly and approachable person, and I have received a lot of encouragement and advice time to time from him. So I am very glad to be here, and I hope to continue to receive it in the future, and wish him a very good health. Thanks. So the title of my talk is a generalization of Roth's theorem in primes, which I think, since I did not give an abstract, it created a confusion in some people's mind. It is not a Roth's theorem in transcendental number theory, which I am going to talk about. It's a theorem in additive combinatorics. So before I state what is a Roth's theorem, let me a few notions. The arithmetic progression of line 3, that is a set of the type A plus D, A plus 2D. So I am in some group, and this is the elements A plus D, A plus 2D. And it is said to be trivial if D is equal to 0, and non-trivial if D is not 0. Okay. So whatever the theorems I will be saying that some set contains a arithmetic progressions of length 3, it will be a trivial theorem if I remove the word non-trivial. It will be non-trivial only if I add the word non-trivial. So given this is a standard notation, given A a subset of natural numbers, we set A and the A intersection 1 to N. And we shall write log K, this notation log K log Kn to be log K times. Okay. So the theorem of Roth says the following, that any dense subset of natural numbers contains a non-trivial 3 terms arithmetic progression. So given any alpha greater than 0, and you take A is a subset of 1 to n with cardinality of A greater than equal to alpha n. So it contains at least alpha proportion of number of integers in 1 to n. Then the set A contains a non-trivial 3 term arithmetic progression provided n is sufficiently large. Okay. So this is a theorem of Roth. So what is the Roth theorem in primes? So this is a theorem due to Bain Green in 2004, that let P be the set of primes, and P1 is a subset of P. And the relative density of P1n in P is at least alpha. Okay. So P1n, when viewed as a subset of 1 to n, is not a dense subset, because Pn is only around n by log n. So this is alpha n by log n. So this is not a dense subset of integers, but P1 is the relative density is positive. Then the set P1n contains a non-trivial 3 term arithmetic progression provided alpha, in fact not only for alpha greater than 0, but he gives alpha should be this square root of log 5 times n by log 4 times, and n is sufficiently large. So in particular, this answers a long-standing question that a dense subset of primes contains a non-trivial 3 term arithmetic progression. So then there was a generalization due to Green and tau. So let me define what is chain primes. We say that a prime P is a chain prime if P plus 2 has at most 2 prime factors, and further P plus 2 has no prime factor less than P to the power 1 by 10. Okay, this can be okay. So we expect that there are infinitely many primes, so that P plus 2 is a prime. We don't know that so far, even with the and there are okay. So but what chain proved that there are infinitely many chain primes. And in fact, it is known that the cardinality of Cn is greater than with some absolute constant here and by log square. So, using the results on enveloping sieve, which is due to Ramare and Zouza, the following result was proved by Green and Tao in 2005, that let C be the set of chain primes and alpha greater than 0 be a real number, and C1 is a dense subset of, so C1 is a dense subset of chain primes, then the set C1n contains a non-trivial theta arithmetic progression provided n is sufficiently large. Remember that now the cardinality of Cn is n by log square n. So then there were for the original question for the primes, this is as I say is a result due to Ben Green in 2004. Then using the results from Green and Tao, which I mentioned about the chain primes, so using the results from that paper, Helfgott and Roton in 2009 improved this result, that now you can take the density to be even smaller. Here there is a log 4 times, and now you can take log n denominator, 1/3. So this was proved by Helfgott and Roton using the arguments from Green and Tao's papers, which I mentioned earlier, along with some new arguments. And then recently, this result of Helfgott and Roton has been further improved by Naslund, and then here the exponent is 1/3, and which he improved to 1 minus epsilon. So as I say, the arguments used by Naslund is so arguments used by Naslund is a modification of the arguments of Helfgott and Roton. Helfgott and Roton computed some second movement of certain functions, and then he computed the higher movements, and that gives the result. So not only Helfgott and Roton improved the results, but the results were much simpler than the original arguments of Ben Green, which happens as the, and this, as I say, and it uses the results from the paper of Green and Tao, which is based on enveloping sieve due to Ramare and Zouza, along with some new ideas. So what we observe that the arguments of Helfgott and Roton gives a more general result. So before I state the result, let me just mention the setting. So let f of x is equal to product of k linear polynomials with ai belongs to z minus 0, so that the no factor is a constant polynomial, and bi's are in integers. We will further assume that the discriminant of f is not 0, so that none of these linear factors are the rational multiples of the other. And f is admissible, that is to say that for every prime p there exists n such that f of n is not divisible by p. So example, so f of x is equal to x into x plus 1 is not admissible, as for every n we will have f of n is even. F of x is equal to x into x plus 2, and x plus 6 will not be admissible, since for every n we will have fn is divisible by 3. But if you take this polynomials, f of x is equal to x, this is admissible. F of x is equal to x into x plus 2, this is also admissible. And f of x is equal to x into x plus 2, x plus 6, these are all examples of admissible polynomials. So just, of course, this is standard, but just for the students, in order to check that some polynomial is admissible, first of all, because this condition seems to be for every prime, but actually you don't have to check it for every prime. First of all, what we know that for all, this will f is admissible implies that for all p the polynomial f mod p is non-zero, which will be true if and only if this GCDs of this ai's and bi's is 1. But that is not, this condition is not sufficient to deduce that f is admissible, as this example shows. Here it should be 4, yeah. Here it should be 4 and here it should be 6. Sorry. Yeah, here x into x plus 2 into x plus 4 is not admissible, but x into x plus 2 and x plus 6 is admissible. And if f mod p for every prime is non-zero, then the condition of admissibility needs to be checked only for p less than degree of f. Okay? Yeah. So let f be non-degenerate and admissible polynomial, as I said. So what is and for any real number z, let p of z is equal to product p less than equal to z p. Then for any natural numbers n, we take this define this set a of n, those n less than equal to n, such that GCD of f of n has no small prime factors. How small is this? That it has no prime factors less than n to the power 1 by 9k plus j. This is not a best exponent which I have taken, but okay, something. So using C methods, we know that cardinality of a f n is roughly around n by log to the power log k n. We know a very good bound for it, upper as well as lower. This can be proved quite elementary using beta C's or. So the theorem says the following: let f be a polynomial as above, means it's a product of k linear factors, and it has a non-zero discriminant and it is admissible. Then there exists sufficiently large natural number and epsilon is greater than 0. Then there exists a sufficiently large number n which depends on this polynomial and epsilon, and a positive constant CFL, such that if you take any b subset of AFN with relative density to be alpha, and alpha is greater than equal to this CF epsilon 1 by log n, then it contains a non-trivial theta mathematical relation. So how it generalizes the result of Eric Naslund, which I mentioned earlier, and as well as Green and Tau. So for getting the result of Eric Naslund, you just take P1. So suppose you have a P1 be a subset of primes. With this, we want to show that P1 contains a non-trivial theta mathematical projection. Then we can apply the above result with P is equal to P1n intersection AFN. Then this assumption that cardinality of P1n is greater than equal to alpha A, P1n will imply that this condition is satisfied. If alpha is as big as this, with some other constant maybe, then we obtain that B using this theorem, that B and hence P1n contains a non-trivial theta mathematical projection. So applying this result with f of x is equal to x, we get a result of Eric Naslund. Now if I apply this result with f of x is equal to x into x plus 2, then we will obtain a result of Green and Tau, which I mentioned. Yeah. So now for the ideas of the proof, I have to go to the board. I'll go to the board, but some things here. So first of all, this set B, which is a subset of integers, but it is usual in this topic that we reduce the problem to the cyclic group of prime order, and which is proved using this following lemma that if you take A is a subset of 1 to n and P is a subprime between this, then it contains a non-trivial theorem arithmetic progression if pi A contains. Okay? It's sufficiently light that I can go to the board now. Or? So we have this set A of n, which is consisting of those integers n less than equal to n, such that let me not write in the mathematical things, but just Fn has no small prime factors. Okay. Huh? Yeah, right. I'll try. So A of n is those set such that f of n has no small prime factors. And now suppose you have been given B, this font size is okay? Yes. And we have been given B subset of A of n with certain properties. Okay. Yeah. Okay. And we want to prove that B with certain conditions, and then we want to prove that B contains a non-trivial theorem of arithmetic progressions. So B is a subset of 1 to n. What we will do is we will choose a prime P between 2n and let's say 4n. We know that there will be a prime in this interval, and and look at B mod P. Okay. So it is not very hard to show that B will contain a non-trivial theorem arithmetic progression if and only if B mod P contains a non-trivial theorem arithmetic progression. Okay. So now I'll assume my subset is a subset of Z mod Pz. Okay. So now a few notations. I think this portion is not so well visible. So given f from Z mod Pz to C, we will write lambda 3f is equal to summation n d f of n plus d and f of n plus 2d. Okay. So if f is an indicator function of some set, then lambda 3f is nothing but number of 3 terms arithmetic progressions in A. Huh? Okay. So okay. So all right. So this is a more generalization of lambda 3 of f. So now for my purpose, I will of course I will be interested in when f is an indicator function of this set B, but for my purpose I will normalize a bit. So given any B subset of Z mod Pz, or let me write down C subset of Z mod Pz, but I will write f of C to be indicator function of C divided by density of C. What is density of C? Is cardinality of C by P. Okay. So this normalization is done in order so that when you look at the expectation of f of C, which is equal to 1 by n summation n f of C n, then that will be 1, because I have taken f of C is equal to indicator function of C divided by density, so the average of fc will be 1. All right. So lambda 3f is this. So what I need to so of course, all right. So now what I need to show is that there is in this lambda 3f there is a contributions coming from d is equal to 0, and if I can show that my lambda 3f is strictly larger than that trivial contribution, then the set contains a there should be a contribution in this sum coming from d not equal to 0, and that would prove that the set contains a non-trivial 3-term arithmetic progression. So what is the contributions coming from so C contains, so if you take lemma if you wish, that C contains a non-trivial 3-term AP if and only if lambda 3f is greater than the trivial contribution will be summation n fcn whole cube, which will be equal to p by dc whole square. So if lambda 3f, if we have a good lower bound for lambda 3 of f c, then we can show that the C contains a non-trivial 3-term arithmetic progression. All right. So in order to prove this result, so in this thing, so we would like to show with and we would like to show this when C is, for instance, if you just consider the primes case, then C is a projection of this first few primes, P1. Okay. So in order to prove this result, what we will require is the following theorem. So let C be a subset of Z mod Pz. Which satisfies the following property, that d of C plus H1 intersection C plus, or maybe I will just prove or give the idea for H2. This can be generalized for HL, whatever I am saying for these things, which will be important, is less than equal to dc square into some coefficients here which will come beta square, then lambda 3 of fc convolved with fb is greater than equal to some function, because in our applications we will not be able to show it with this constant equal to 1, but with some other constant. So there will be a constant which will depend on this c and beta, times p square. Okay. But there are two things. Okay. So one thing is that if you ignore for the time being this f, now the point is that the set which we are looking for AFN satisfies such a bound. Because the cardinality of, so the point is that for those, that a number is a prime as well as n plus h is a prime, that the probability is not, a number is a prime, the probability is like 1 by log n, but a number is a prime and n plus 2 is also a prime, is the probability is not like 1 by log n, but it is like 1 by log square n. And this can be proved using C methods, the upper bound. Okay, so we can show that the cardinality of B intersection B plus H here is so cardinality of B is like some n by log to the power kn, and this will, we can show that that is less than or equal to n by log 2 kn. So if we look at B mod P, the similar condition is true. Okay? I am cheating slightly, but because it's here, that because I have to, this is not quite true, therefore I have to use some other trick to make it true. But more or less that is the case. And that will prove that lambda 3 of FC convolution FB is big, beta is big. Now we have to prove that the lambda 3 of F is greater than P by DC square. So, and here is a P square, so that's quite a good bound. Once we can show this theorem. Okay? But we are interested in, so there are two problems. One problem is that to prove this theorem. The another thing is to estimate the difference between lambda 3 of FC minus lambda 3 of FC convolution FB. Sorry, this. So I will find a suitable set A so that if I take, so lambda 3 of FC minus FC convolution FA, so when I take this C is equal to this B or B bar, whatever it is, that lambda 3 of, I will find a suitable set A so that lambda 3 of FB convolution FA is large using this theorem, and then I have to estimate the difference between the lambda 3 of FC minus FC convolving FA. If I can show that lambda 3 of FB, that will give me a lower bound for lambda 3 of FB, and which will give me, and then if I can show that the lambda 3 of FB is greater than this, then I am done. So one of the properties which I am saying the primes which is used for from the primes is that the number is a prime or number is an almost prime, this generalized almost prime if you wish, is the density becomes density n plus h is a prime is like the density of the primes square and not. All right. So first of all, I should give a proof of this particular result, that lambda 3 of So in order to prove this result, what we need is a Van-Avedis theorem, which says the following, and Van-Avedis type theorem. So One-Navadi's theorem will not be quite enough for this, but we need a certain suitable modification of One-Navadi's theorem, and that is where the novelty of Helfgott and Roton lies. So One-Navadi's theorem says the following, that if you have let eta greater than 0, d greater than z mod pz, sorry, d subset of z mod pz with cardinality of d greater than equal to eta p, then lambda 3 of indicator function of d is greater than equal to eta by 2 p into p minus 1, sorry, some function of eta, let me just note, into p square. For the purpose of this, of course, when I am getting the result, it will be important for me to know what exactly g of eta is, which can be given a lower bound for it, and better lower bound if you have a better and better Roth theorem, whatever it means. But for the purpose of this talk, let me just ignore that fact. Okay? So corollary of this is, since we are not interested in the indicator function of d, but a suitable normalization of indicator function of d will be that if you have a let f from z mod pz to r plus is a function with E of f is equal to 1, which is the case in our application, and but what is not true is norm of f infinity is less than equal to some, so f is bounded. Then lambda 3 of f is big, some function which will depend on t times p square. Okay, but in our case you see that our f of c is indicator function of c by dc, and dc is cardinality c by p. So in cardinality c by p, so the cardinality of c will be, let's say if it is set, c is a set of primes, then it is like 1 by log p. That means f of c, the bound will be like log p. So f of c will not be a bounded function. And for that reason, we cannot use this corollary. This corollary is quite easy to prove, but unfortunately one cannot use this corollary in order to prove our results. So what one needs in order to prove this corollary is the following, that so suppose you have another, again a function, positive function, non-negative function, and E of f is equal to 1, and you have a f of L is bounded by some c by beta or something. So the Lth norm is bounded. Then lambda 3 of f is large, some g c beta p square. Okay. In our application, again, if you try to apply for f of c or f of b, the Lth norm will not be bounded, but we can choose a suitable function so that when you take the convolution of it with something, then the Lth norm will be bounded. And in obtaining a bound for this convolution is where we will use the fact that the density, when this is n is a prime and n plus h is a prime, is the density is not like a 1 by log n, but 1 by log square. this result is quite actually easy. So first of all, let me just give a proof of this. So let me define D is equal to those and belongs to Z mod Pz. So is that f of n is greater than half. Okay. Then since E of f is equal to 1, then E of f is equal to 1 by P summation n belongs to D f of n plus 1 by P summation n not in D f of n. And this contribution will be small because we have assumed that for we have taken in D all those f n greater than half. So this is less than equal to, here f of n will be at the most half. And so so this will be, and there are at the most p number of terms. So this is this second contribution is at the most half. This particular thing, because f of, for all n there is f of n is less than half, and there are at the most p many values. So that will give that 1 by P summation n belongs to D f of n is bigger than half. So what we get is that 1 by P summation n belonging to D f of n is bigger than half. And then you use that this is less than equal to norm of f2. I'm using the second moment here into cardinality of D by P to the power half. Just using Cauchy-Schwarz, because this is 1 by P summation n belongs to D f of n. This is less than equal to 1 by P summation n f of n square half into 1 by P summation n belongs to D 1 to the power half. And that gives you a lower bound for the cardinality of D. And once you have a lower bound for cardinality of D, then lambda 3 of f, since f is a non-negative function, it is greater than equal to summation n D f of n plus 2d d f of n plus 2d, and such that you are restricting here the sum n plus d n plus 2d is contained in D. So number of three terms arithmetic progressions inside D. But now that because of, if you have a good lower bound for the upper bound for the second movements, this will show that D is a dense subset of Z mod Pz, and therefore you will have a, then you can use Von-Everdy's theorem to get a bound for the for the getting a lower bound for this quantity, and that will give you, okay, I'll